everyone, welcome back to my course. So in the previous session we looked at, or we introduced ourselves to the concepts of equilibrium and kinetics, and also I believe we looked at some of the aspects about identifying which particular state or characteristics such as kinetics is important. For example, we looked at trying to identify is a system under equilibrium control, kinetic control or mixed control and so on. So during the course of the next few sessions, we are going to delve into greater depth or detail with respect to equilibrium now, right? So I believe we already looked at some of the aspects or examples relevant to the importance of equilibrium. I believe one example we looked at, I think in the previous session, was that we looked at trying to identify the maximum heavy metal removal at a certain pH, let's say, right? Heavy metals can be precipitated out, and given the relevant pH and the ligand concentration, you can estimate to a great degree of accuracy the greatest possible removal, or the highest percentage removal of the relevant heavy metal or mixture of heavy metals. Yes, that's one particular example, but that's applicable in equilibrium is applicable to any particular engineered or natural systems. So we are going to move on, and I believe we are going to also discuss about what drives or defines equilibrium now, right? I want to know, let's say, is a particular system feasible or not feasible in the first case. So I believe we started discussing the aspect called Gibbs energy or Gibbs free energy or change in Gibbs energy now, right? So let's look at the definition first, right? And most people are aware of this. So delta G equal to delta H minus T delta S, right? So delta G is the change in Gibbs free energy or change in Gibbs energy of a particular system. Delta H, change in enthalpy, more or less gives you an idea about the heat energy being released or being taken into the system, and delta S gives you an idea about the change in entropy. S more or less, let's say, right, the greater the disorder, right, the greater the entropy now. And in general, delta G is a state variable. What does this mean, right? So in general, we know, let's say if this is G, how do reactions occur? Let's say you can visualize them as if it's going from state G1 to G2, right? So they are going to fall down the ladder. You can visualize that, right, from state G1 to G2. So what when we say delta G or Gibbs free energy is a state variable, what does that mean? It doesn't depend upon the path it takes to go from 1 to 2, right? It's independent of the path it takes for the system to go from state 1 to state 2. That's what we understand when we say we call that call Gibbs free energy a state variable, right? And again, one other aspect to consider, or two other minor aspects, is that delta G changes in the same direction as, or G changes in the same direction as H, or change in enthalpy, but delta G changes in the opposite direction as change in entropy, right? So that's something to keep in mind and which we are going to discuss later on. Yes. So let's move on, and I guess we are going to talk about process feasibility now. So what defines, or how can we understand, let's say, or relate the change in Gibbs free energy to equilibrium or the relevant concepts that we come across in nature or in engineered systems, right? So you want to know, let's say, a particular reaction, is it feasible? I mean, would it go forward or no, right? So for that, in general, we always have learned to look at delta G, right? And what is that equal to? I guess we know that that's equal to delta H minus T delta S. And in general, I guess this is common knowledge. So whenever delta G is less than 0 or is negative, we say that the process is feasible. When delta G is greater than 0, we say that the process is infeasible. And when delta G is equal to 0, we say that the system is at equilibrium. So let's just try to understand these aspects for a second, I guess. So in general, we will again go back to the previous figure that we looked at. So if I have G here, and let's say if I am trying to indicate the two states, so the initial state is G1 and the final state is G2, right? And obviously here the change delta G is equal to G2 minus G1, and as you can see, state G2 or state 2 is at a lower energy state compared to state 1 or G1, right. Thus, it is negative, and as you can see, you know, if you can visualize that, it is falling down the ladder, right, the system. So, thus this process is feasible, right, this is feasible. And obviously, though, the second aspect that we just looked at, or we just have here written down, I guess, let us say G2 is at a higher energy state and G1, or pardon me, 2 is at a higher energy state and 1 is at a lower energy state. So, delta G, right, which is G2 minus G1, let us say, is going to be positive, right. So, system cannot move up the ladder, right, again for visualization purposes I am saying it is moving up the ladder. So, obviously, that means that the system is infeasible, but as you can visualize, the system can go from G2 to G1 though, right, the reverse reaction is feasible. This is what we can understand from here. So, this indicates that the reverse reaction is feasible, but the reaction that goes from 1 to 2 is infeasible, right. And obviously, the third aspect I guess is self explanatory. So, when both the states are at the same energy state, let us say, or energy levels, whichever way you want to understand that, there is no, what do we say, further intensity to either move up or down the ladder, pardon me, move down the ladder. So, we can say that the system has reached the maximum extent possible at that particular conditions of temperature and pressure. So, it has traveled the, so we looked at equilibrium as how far can the system go, right, at the given conditions of temperature and pressure. So, when G1 and G2 are the same, it means the system has reached equilibrium or traveled the farthest extent possible, right, or reached the maximum extent possible under the given conditions of temperature and pressure. So, again, so delta G is equal to delta H minus T delta S, right, and now we are going to look at the individual terms in greater detail, and pardon me, I guess. Okay. So, again we have delta G equal to delta H minus T delta S. So, again let us look at how these apply to, let us say, delta H and delta S and so on, let us say, right. So, in general, H obviously, as we talked about, or delta H is decrease in enthalpy. Enthalpy means it favors the reaction, right. So, what does that mean though? So, decrease in enthalpy means delta H is negative. When delta H is negative, right, that promotes delta G being negative, right, and that is what you can see from this particular reaction here. When delta H is negative, it promotes delta G being negative, that means it favors the reaction now, right. So, what does delta H negative mean? Let us say, again, if I have here, again this is just for visualization purpose, right. So, here let us say H1 to H2, right. So, heat energy will be released in this process, delta H is equal to H2 minus H1, right, and as you see that is negative, yes. So, what does this mean though? The energy that is stored in state 1, let us say, is going to be released as heat energy here. So, whenever delta H is negative, what does that mean? It is an exothermic reaction, and obviously what does that mean? That means release of heat energy, yes, and obviously again increase in entropy, or what does that mean? Delta S being positive, or delta S being positive, right, promotes delta G being negative, yes, and that favors the reaction now, right. So, let us look at an example here. I have an example here, let us look at what this means. So, in general, entropy, I guess, gives you an idea about the degree of disorder in the system. So, again I am using a lot of layman's terms here, so that people, it is easier for the students or the audience to understand what I am talking about. So, for example, let us say if a solid is changing phase or transforming to a liquid phase, the degree of disorder or the entropy will increase. And again, if liquid again further transforms into a gaseous phase or gas, let's say, not gaseous phase, pardon me. So it's again going to increase the degree of disorder in your system. Or if there is an increase in number of moles, let's say, of this system. So what does that mean? So let's say initially I had 1 mole, and that either due to combustion or any other relevant reactions which we are going to discuss in greater detail, now transforms into 2 or 3 or so moles. You see now you have an increase in number of moles. That more or less means there is a greater degree of disorder in the system, right? And that means again delta S is positive, right? In the second state there are more number of moles, right? So delta S is positive, right? And again that means delta H, delta G will tend to be negative, and that obviously again favors the reaction as we defined it, I guess, right? Reaction defined as in this case I believe we have been talking about going from state 1 to state 2, right? So again one final example here. So we have NaCl in the solid form, what we say, dissociating into Na plus and Cl minus, when it's dissolved in water, obviously the aqueous phase, AQ stands for aqueous phase, which we in general indicate when we have a compound dissolved in water now, right? And here we have, let's look at the delta S value at the standard conditions. Standard conditions, this particular nomenclature indicates standard conditions. So change in entropy at standard conditions, and the value that I have here is 43.4 joules per Kelvin, right? And obviously if someone asks you to what do we say, guess what's the sign here, you can obviously say it's going to be positive, right? Plus 43.4 joule per Kelvin. And why is that? Obviously now you have a solid phase and it's dissociating into what do we say, aqueous phases, and more importantly initially you had 1 mole and now you have 1 plus 1, 2 moles. So the disorder, or the greater the disorder, we know that the delta S is going to be positive. So that's one example that you would see. Yes. So another example that I have is 2NO2 in the gaseous phase, and this it seems can be at equilibrium with N2O4 in the gaseous phase. So now if I look at the change in entropy of this system, and the magnitude looks like is 175.83 joules per Kelvin now, right? And someone asks you, to think of what the signage is going to be. So here both are the gaseous phase, so we can't really draw many conclusions from there. But if I look at this particular aspect, as in initially I have number of moles as being 2 and now I have 1 mole here. So right, so the degree of disorder is less. So what does that mean? Delta S is going to be obviously negative here, and this in general would not favor the reaction to go through, right? So obviously you need to look at the standard change in enthalpy to be able to give a final call or take a final call about delta G either being positive or negative, right? Anyway, a few examples here that we looked at. So let's see what we have next. So okay, so we talked about the driving forces for equilibrium, let's say, or for system to reach equilibrium, pardon me, right? We looked at Gibbs free energy. So now we are going to move on to look at applications to reactions now, right? So you now let's say you can calculate delta G values, but we are going to look at it in great detail about how to relate that to a particular system, or let's say a system is going from state 1 to state 2. You want to be able to relate that. So again, before we go further though, obviously we need to look at what's the Gibbs energy of a mixture, right? Here keep in mind we are not talking about change, but we are just talking about the Gibbs energy of a mixture. What is that, or how do I calculate that? So let's say in the mixture I have compound A, B, C, D and so on, I number of compounds. So how do I calculate that, let's say, right? And that obviously can be calculated by summation of Ni Gi bar. Ni is number of moles of compound I, right? Gi bar, a new concept I guess is Gibbs energy per mole of compound I, and that is actually also equal to mu I, which again is a new term, is the chemical potential of component or compound I, right. So, now we have a new term, what do we say, mu I, or the chemical potential of I. So, we are going to discuss that in a bit more detail, right. So, what would you understand when, let us say, somebody says someone has, let us say person A has potential, right, and here again we are talking in layman's terms. So, what do you understand, let us say, when somebody has potential now, right. So, it means the person or the system, let us say, has the capacity, right. Again these are all layman's terms, so you do not need to note them down obviously. Capacity to do something, let us say, a very generic term, to do something, right. Yes. Again, so I think a better example would be to look at, let us say, potential energy, let us say. So, the higher the potential, the higher the capacity to be able to do something worthwhile, let us say. So, you can draw a corollary here or look at the analogy here, right, and you can think of chemical potential in the same way as in a mixture or in with respect to reactions either going forward or back, let us say. As we know, how do reactions go through? Let us say, we know that, with G1 and G2. So, we know that the system would fall down the ladder from G1 to G2, right, and we know that the G of the mixture, let us say, what is that equal to, I guess, summation of Ni Gi bar, which is also, as we just looked at, Ni mu I guess, right, we can even derive this, right. And what does that mean now? You see that whenever the chemical potential is high, let us say, right, there is greater potential for the system to fall down the ladder and for the reaction to proceed through. So, the greater the potential of the system, it has a greater tendency, or it can, let us say, go down the potential and make the reaction favorable, that is just for your purpose of understanding now, right. So, again a minor aspect that we are going to look at. So, in general we call, or we can say, potential equal to right, and what is this equal to, I guess, d G of the system or mixture, right, by d Ni, and that would be equal to, as we just looked at here, I guess, what is that equal to, I guess, d pardon me, summation of Ni mu I by d Ni, and that obviously is equal to mu I guess, right. So, that is what we are trying to look at. So, potential, chemical potential, that is how it comes about, yes. So, again the take home message is that the higher the chemical potential of a particular chemical, that more or less relates to higher energy state or Gibbs energy of the mixture, and that would mean a greater tendency or potential for the reaction to go through or fall down the ladder, which more or less translates to the reaction going forward, right. So, let us see what we have next, I guess. So, the next aspect I guess we have is applying this to the Gibbs energy change for chemical process, or obviously for a reaction now, right. So, here we are going to look at what we say, trying to, so for a very small change, let us say, or infinitesimal change in reaction, let us say, I want to be able to calculate the change in Gibbs energy, or how is Gibbs energy going to be affected by a small change or infinitesimal change in the reaction now, right, or when the reaction has gone through by a small extent now, right. So, first let us take an example of a reaction here, a generic example. So, here we have stoichiometric coefficient of A times compound A, stoichiometric coefficient B going to C. So here we have the stoichiometric coefficients mu A, mu B, C and mu D, right. So A plus B goes to C plus C and D, pardon me, and moles of A, I guess, stoichiometric coefficient, you have that, let us say. So this is the general reaction now. So let us define a term, let us say, saying that the small change in reaction, right, is the Greek term Xi, right. I guess my handwriting is very poor, okay, Xi. So for a small change in the reaction, let us say, I want to be able to equate that to the change in moles of compound A, B, C and D, right. Let us say the change in number of moles of A, B, C and D. So how do I do that, let's, because I am still missing a few terms, right. So how do I do that, let us see. So obviously as people are aware, we can normalize that by looking at the stoichiometric coefficients, right. And obviously because A and B are being lost and C and D are being formed, we are going to have to use the relevant signage here, right. And so this is something that we have here, and we are going to use this later on. So let us say I am going to call this equation 1, let us say, right. So next aspect is we want to look at for a small change in reaction, what are we looking at? Gibbs energy of the system, how is it changing? So obviously we first need to calculate the Gibbs energy of the system or the mixture initially, right. So what is that equal to? I think we looked at that earlier, equal to Ni mu I, right, and that again is equal to what now? Anyway, we do not need to go into greater detail here, or I guess yes, it is worthwhile, Na mu A plus Nb mu B, right, plus Nc mu C plus Nd mu D, right, yes, and we have that here. And so obviously again what are we looking at? This is the initial what do we say, Gibbs energy of the system or the mixture, this as in this particular term or set of variables here. And what do we want though? We want to observe for a small change in reaction, how is the Gibbs energy changing, right. And we already defined for a small change in reaction as dg, right. So if I take the derivative here, dg of the system dz, and that is equal to what now? D by dz equal to d by dz of Na mu A plus Nb mu B plus Nc mu C plus Nd mu D, right. And now I guess let us try to get this right here, and that would be equal to what now here please? Mu A into D by Na of dz plus mu B into D Nb by dx plus mu C dnc by dz plus mu D into derivative of what now? Number of moles of D for a small change in or extent in reaction, I guess. So right, and what do we see here? Let us try to relate these particular terms to what we just calculated here in this equation 1, right. And what do we get here? I guess we are going to get dNA by dx, or derivative of number of moles of A by number of by for a small change in the reaction is going to be equal to minus mu A, right. So that obviously is going to be minus mu A UA plus, again what is this? This is a stoichiometric coefficient, and this is the chemical potential of A, right, and again not plus here, minus mu B plus nu C mu C plus nu T mu D, right. So instead of going on to a fresh page and then losing track of what we are up to here, let us try to summarize what we have looked at thus far here. And so obviously this is the take home message, so I am going to do that here on this part, let us say. So here we have now dg of the system dx is equal to what now? Summation of Ni mu I of the products, not Ni, pardon me. So obviously that is a bit of a mistake there. Summation of the stoichiometric coefficient, I guess, right, Did we mess something up here? No, let me just have a look at this now. Mu A, okay, seems fine here. Mu I of the products minus summation of mu I of the reactants here, right? So this is what we have here. And so let's look at, let's just review what we have up to. We are trying to calculate the change in Gibbs energy for reaction for a small change in the reaction, or when the reaction has gone through to a small extent. So that we define by dxz, and we tried to relate that to change in the number of moles of your particular compound here, right? And we, in reaction 1, we normalize that by the stoichiometric coefficients, yes. So here we are trying to define the change in the number of moles of each compound with the extent of the reaction. And then obviously, because we are calculating the change in the Gibbs energy, we first need to define or calculate what the initial Gibbs energy of the mixture is. So that we looked at it earlier, and so upon expansion, this is what we have here, yes. And so this is what we are trying to calculate all along, the change in Gibbs energy of the system for a small extent or change in the reaction. And so I guess we have that here, and transformation and looking at equation 1, we came up with this. Now what is that again? So let's go on to the next page and then write that up again afresh. So dg of the system, dx, or more or less change in Gibbs energy of system for a small extent in or infinitesimal change in the extent of the reaction, is equal to what now? Stoichiometric coefficient of I, Vi mu I of the products minus Vi mu I of the reactants again, right? And so this obviously is equal to what now? Delta G, right? So obviously, if you look at it, when will delta G be negative? Obviously, when this term is going to be greater than this term. Again, higher the chemical potential, I guess, they would like to fall down the ladder. So that's what we are looking at, but that's not greatly applicable here, but that's an analogy I'm trying to draw here, right? So when this term is greater than this, so that's what we are going to have here, when that's going to be negative. And where did we have that here? I guess here. A and B are the reactants, and C and D are the products here, right? So let's try to have this in a graphical format so that we can understand this better, right? So here we are going to have a particular figure here, and here we are going to have G of the system, and X is the extent of the reaction. And for example, let's say this is how the system can behave, right? And this is what we have here. And so let's say we are trying to look at delta G, or more or less dg by dxz. So more or less, what does dg by dxz mean? It means the slope of this particular graph or system here. So let's say I'm identifying 3 particular aspects here, right? And in this case, as you see, delta G or dg by dxz is going to be negative, the slope is negative. Here it's equal to 0, and here it's going to be positive, right? So what do you understand here? So in this particular phase, let's say when delta G is going to be negative, or the slope is negative, let's say, you are going to have a reaction that is feasible. Again, here we have G, or the Gibbs energy of the system, in on the y-axis, extent of the reaction X on the x-axis. So think of this now. Let's say, again for visualization purposes, so if this is G1, it can fall down to G2, right? And that's how the reaction can go through, right? And that's where you see delta G being negative, or dg by dxz being negative. So obviously, when it's equal to, or the slope is equal to 0 at this particular point, let's say it has reached equilibrium, yes, and now there is no tendency for the system either to go from G1 to G2 or so on. It has reached the maximum extent possible. Again, what's happening here though? Here let's say G2 is at a higher energy state. Let's say, again I'm using layman's terms please, and G1. So the system can't go from G1 to G2, but if it wants to, not if it wants to, the reaction that takes the state from 2 to 1 is feasible, but not from 1 to 2 though, right? That's what you understand here when we say delta G in this region here is positive. Again, you see the positive slope here, and again you can relate that to what we just looked at earlier, dg of the system with by dz, right? And so that's what we just looked at here. So hopefully this should give you a good idea about what we are talking about. So again, you don't need to what do we say, mug this up. This is for an understanding of the basic principles involved here, right? So again, we are going to tie everything up. Delta G negative means the reaction is feasible. Delta G being positive means the reaction is not feasible, or the reverse reaction is feasible. And delta G equal to 0 means the system is at equilibrium, right? Okay. So let's move on and see what we have next. Okay, so next I guess we are going to calculate the Gibbs energies now, right? So you are trying to calculate delta G's, right? Or we have learned how to look at delta G until now and how to relate that to reactions, how to relate that to mixtures. And again, to take a bigger view, not a bigger view, pardon me, a holistic view, right, and look at the bigger picture. What are we talking about? Let's say, let's just summarize briefly. So we have, we introduced ourselves to equilibrium and kinetics, and then we started delving greater into the concepts of equilibrium, and there we introduced the concept of change in Gibbs energy delta G, and in that aspect we applied that to reactions, and we also applied that to mixtures, right? And now we are going to further talk about how to calculate Gibbs energies of the system now, right? And we will talk about kinetics later on, maybe a few sessions down the line. So again, I am just giving you this information so that you will have an idea about what it is that we are talking about in relation to the bigger picture again. So we are still talking about equilibrium here, right? So how do you calculate Gibbs energies, I guess? So before we go further, we need to understand that there are two aspects involved now. One's the standard conditions, and the other would be the non-standard conditions, right? So obviously we are going to first discuss the relevant aspects or how to calculate Gibbs energies at the standard conditions, and then we are going to move on to the non-standard conditions. So standard conditions, how do you define them? So we could say that when the temperature is 25 degrees centigrade and when the pressure is equal to 1 bar, and now we have a new term called activity. Activity of the particular compound is equal to 1. For example, understand activity as concentration for now, right? We are going to go through that later. Activity is not the same or equivalent to concentration, but for now, think of activity as ideal measure of ability of compound to react. So it gives you an idea about the ability of a particular compound to react, right? In general, let's say we are going to, you can for now think of it as the concentration of a particular compound, but we are going to see why we need to look at activity later on. So when do we, so standard conditions, what are they again please? Temperature being 25 degrees centigrade, pressure is 1 bar, which is more or less equal to, I guess, 1 atmosphere, but not so, you can look this up. And when we say activity or let's say activity which we can approximate by concentration in some cases is equal to 1, right? So again, now we need to calculate Gibbs energies, right? So in general we are always concerned with delta G values though. So what is this here? We are looking at a difference here, G2, pardon me, G1 minus G2, right? So for that, we obviously need the reference, right? So it's like calculating the mean sea level, right? You in the railway stations and such, you would have come across a particular term called the MSL below the nameplate, or where you have the relevant signage, let's say, you would have seen a particular term, MSL, so on. So I guess obviously it's the mean sea level. For that, I guess they set the sea level as the reference. So in the same case here, in our delta G, or when we are looking at changes in the Gibbs energy, we need to set a reference to. So here we said that the Gibbs energy of formation of elements, is equal to 0. So here we have two aspects, I guess, that we are coming across, new terms. So, Gibbs energy of formation of a particular compound or element at standard conditions. So, in this case though we are setting our reference as the Gibbs energies of formation of elements at the standard states, we are setting that as being 0. So, what does that mean, or how will that help us now? Let us say I have element 1 and element 2, you know, forming let us say compound, I guess, right. And since we set the Gibbs energy of the system of the elements to be 0 at the standard conditions, and if you want to calculate delta G of this particular reaction, that is equal to what now? I think we looked at this, right, Ni Gi bar of what now, the products minus Ni Gi bar of the reactants, right. So, that would be equal to here what now? So, here let us say we have the number of the moles or stoichiometric coefficients are 1 here for all the 3 cases here. So, that is more or less going to be equal to the Gibbs energy of formation of compound I minus Gibbs energy of formation of this element 1 minus Gibbs energy of formation of element 2, right. So, but as we just discussed, we set these 2 terms as being 0. So, this will now give us the, or the delta G of the reaction would give us the Gibbs energy of formation of, again all these are at standard conditions. So, let us keep that in mind here, right, of compound I. So, at the standard conditions, if you can measure the change in Gibbs energy, you will thus be able to calculate the Gibbs energy of formation of your compounds. And in general, all these are available in your standard tables in most textbooks, and certainly in the references that we talked about, right. And if you are not sure which one is an element or which one is a compound, you can again refer to those standard tables, and there you will have the relevant information. So, here I believe I have one example, and let us look at that. So, here let us say we have graphite, carbon in the form of graphite let us say, and 2H2 gas going ahead to form methane CH4 in the gaseous phase. So, how do I calculate the, so these 2 are elements here and this is a compound here, right. So, I am just trying to draw a corollary here. So, how do I calculate the Gibbs energies, I guess, of the relevant compounds? So, delta G naught change in Gibbs energy of this reaction at standard conditions is equal to, as we know, Vi mu I, or pardon me, let us not use mu I here, we are talking about Gibbs energy. So, we will talk about Gi bar or Gibbs energy of the products minus the summation of Vi Gi bar of the reactants. So, that is equal to what now here? So, here Gibbs energy of formation, which more or less in this case is equal to the molar Gibbs energy, I guess, of CH4 minus 1 into, what is this now, 1 is the stoichiometric coefficient here, right, 1 into what do we have here, Gibbs energy of formation of graphite minus 2 times Gibbs energy of formation of hydrogen, right, in the gaseous phase, obviously hydrogen gas, pardon me. So, as we just discussed, these 2 are elements, and so hydrogen and graphite are elements, and thus the Gibbs energy of formation of those elements we set as 0. So, these 2 terms would now be 0, and so the delta G of the reaction standard conditions is the same as Gibbs energy of formation of methane. So, if you can calculate this, you can calculate CH4 or such. So, what will this help us? So, from the elements, again I am coming back to the initial equation, you can calculate the Gibbs energy of formation of most of the compounds, right. So, once you have most of the compounds, let us say C1 and C2 and so on, then you can again, so now let us say you have the Gibbs energies of formation of C1 and C2, right, and C3 and C4. So, then you can go ahead and without measuring it, I guess, calculate delta G values at standard conditions of your relevant reactions. So, I believe I have one last example before we wrap up the class. So, here I guess we have CH4 plus 2O2 goes to CO2 plus 2H2O. So delta G naught, or change in Gibbs energy system at standard conditions, is equal to sigma of mu I Gibbs energy of formation of I product minus summation of mu I Gibbs energy of formation of I at standard conditions of the reactants. So right, so delta G naught or delta GR naught, whichever way I guess, equal to Gibbs energy of formation of carbon dioxide, right, at standard conditions, and plus 2 times Gibbs energy of formation of H2O at standard conditions minus Gibbs energy of formation of what now, methane at standard conditions, and 2 times Gibbs energy of formation of the hydrogen gas, right. And so you can identify which of these are elements, I guess, and you already have the Gibbs energies of formation of some of the compounds, and then you can end up calculating the delta G of the reaction, right. So I guess we'll just summarize what we have been up to for today, right. So we started talking about equilibrium in greater detail, and then we talked about how it depends upon delta G, and we looked at delta G being negative, positive, and 0. 0 equates to obviously equilibrium, and then we looked at some of the driving forces as in standard or change in enthalpy and entropy. Enthalpy gives us an idea about the heat energy, let us say, or energy in the system, and entropy about the degree of disorder. So again we try to link change in enthalpy or change in entropy to change in Gibbs energy, and I believe then we have moved on to talking about Gibbs energies of the mixture. So G system or of a mixture, right, what is that equal to? I believe it's summation of Ni Gi bar or Gf bar, and that we said is also the same as sigma of Ni mu I is the chemical potential, right. And then I believe again we tried to link that to change in Gibbs energies of during a reaction, right. I believe we calculated dG by dxz, and then we looked at the relevant changes and so on, right. So I guess with that I'll wrap up the class for this session, and thank you.